So as an interesting application of the variational principle, I want to just demonstrate to you beyond any reasonable doubt that any attractive one-dimensional potential has a bound state. So that's the statement that we want to prove, and I will go ahead with the proof, set it up, and I will take it to its final conclusion by being fairly precise mathematically about all that we're doing. So the statement that we want to show is that every attractive potential has a bound state. All right, so one of the important things that we have to clarify here is what do we mean by an attractive potential? This may not be so obvious, so we're going to state it very carefully. But by an attractive potential, I mean a potential that goes a v of x such that the limit as x goes to plus or minus infinity of v of x is 0. So first of all, it asymptotes to 0 in both sides. So the second thing that I will want to say is that it can be a complicated potential. I will assume it's piecewise continuous, the potential. So no delta function. So piecewise continuous. So it's continuous except at a few points where it can be discontinuous. And let's, for simplicity, avoid delta functions. Then I will also assume that it's never positive. So the potential is negative everywhere and goes to 0 at plus minus infinity. That actually means that the potential is minus the absolute value of the potential. The fact that it's never positive means it's always negative. And for negative numbers, the number is minus its absolute value. So here is how a potential could look. In that case, you could have a potential that goes like this, then it goes here, and then has a dip, fall, and then it goes like that, and then it could be something like that. I could make it a little more general by making it look like this, perhaps. So that's a typical thing. Piecewise continuous, it jumped here. Never positive, it's always below, and it asymptotes to 0. So this will be what I mean by an attractive potential. And you could try to think of potentials, or if you could relax some of these conditions, but with these conditions, I can prove that this potential always has a bound state. So, for example, the harmonic oscillator potential doesn't fit this one because it goes up to infinity. Those have bound states, and it's easy to prove them and to calculate them. But here you have the general thing. And what can happen in physics is, and it will in fact happen in 3 dimensions, that if you have a potential that is attractive in this sense, is 0 everywhere and then negatives in some place, it just may not be strong enough to create a bound state. It's a funny thing. It's a very interesting thing that happens in 3 dimensions. But in 1 dimension, for a one-dimensional potential, here is x and here is v of x, this will not happen. Each time you have an attractive potential in this sense, defined to be like that, you will have a bound state. So in order to do this, we must find, to prove this result, what we want to show is that the ground state has negative energy. You know, a potential like this, if you had an energy level that is greater than 0, it would be a free particle, an unbound particle. It could move all the way to the right or to the left without having to have be a bound state that decays. So in order for us to have a bound state, you need a state with negative energy. So since the potential goes to 0 at infinity and the energy will be negative, at some point the wave function begins to decay, and it satisfies the property of a bound state that the wave function vanishes at plus minus infinity. So what do we have to do? We have to find, to prove this, we have to find a normalized trial wave function, psi of x, such that the expectation value of the Hamiltonian on this psi alpha, which is the integral dx psi alpha of x, it's going to be real. You remember, for a one-dimensional potential, you can choose your wave functions to be real. So this wave function I'll take here to be real, h psi alpha of x, such that this expectation value is less than 0. If this is true, you know that the energy of the ground state, in general, by the variational principle, is less than or equal than the expectation value of the Hamiltonian on any trial wave function. That's the variational principle. And if you find some wave function for which this expectation value is negative, this would be less than 0, and you would have success. You would have shown that the energy of the ground state must be less than 0. So, what we have to do is prove that. Now, let's think of the Hamiltonian and express this fact. So, what is the Hamiltonian? Minus h squared over 2m d second dx squared plus v of x. Now, we have to compute this expectation value of the Hamiltonian. Now, it will be useful for us to use this property that v of x is minus absolute value of x. So I will change that here. Instead of putting v of x, I will put minus the absolute value of x. So the expectation value of the Hamiltonian will be given by the expectation value of this part that we call the kinetic operator and minus the expectation value of this part. So the expectation value of the Hamiltonian h will be the expectation value of the kinetic term minus the expectation value of this v of x absolute value on psi alpha. All right, so we have our work cut out for us. We're trying to find some wave function in which we can show that this expectation value is less than 0. So let's look at what is the expectation value of t. Well, I'll probably go here. The expectation value of t in psi alpha is the integral. Now, for this term, the the usual trick is to do integration by parts, and therefore to take this ddx squared and flip one into the other derivative. So this will become a plus h squared over 2m integral dx of psi alpha prime of x squared. So the two psi alphas, each one will be acted by one derivative, and the sign, because of the integration by parts, has been cancelled. So this is what we have to compute. The other integral, the expectation value of the absolute value of the potential on psi alpha, will be just equal to the integral dx of psi alpha squared times the absolute value of v of x. And now it's time to choose some trial wave function. So I should choose a normalized wave function and try to understand why this term will overwhelm the positive term. This t is manifestly positive. It's the integral of a square of a number. This v is manifestly positive here, so with a minus sign, I need to understand why this term is bigger than that, or how can I make sure that it's bigger than that. So let's take a psi alpha. I'll write it here. Psi alpha of x, which will be an exponential minus 1/2 alpha x squared. But I have to normalize it. And if I normalize it, the normalization factor needed is alpha divided by pi to the 1/4. That you can easily check. All right, so now I have to do these integrals. Well, that's a good exercise for you. You've probably we've done a similar integral before when we looked at some example of the variational principle. And here, this integral is easily done, and it just can be done completely. So this is known, and the answer is h squared alpha over 4m. Okay. Then the other term, it's an integral that I can't quite do, but we can leave it, simplify. You get the psi squared gives you a square root of alpha over pi. And then you'll have the integral from minus infinity to infinity of e to the minus alpha x squared v of x dx. The psi squared has been put there. So that's the integral we have to do. Now, what is success in our goal? Success is to show that this thing is bigger than this. That this number, because it's just a number, is bigger than that. But it will only be true for some values of alpha, and that's a delicate thing. We have to understand that there's some values of alpha for which this term is bigger than this. And it may not look all that obvious. This is the square root of alpha, and the square root of alpha looks smaller than this one. But let's try to make this clear. So what do I want? That the v term is greater than that. So let's form the ratio. Consider the ratio of v, expectation value, over t, expectation value. Well, the integral is there. It's in the numerator, so you'll get the integral from minus infinity to infinity of e to the minus alpha x squared v of x dx. And as far as the coefficients are concerned, you get the 4m over alpha squared. So the coefficient, I'll just copy it from here, is 4m over square root of pi h squared 1 over square root of alpha. So by dividing v over t, the important thing is the alpha. V divided by t, you get the square root of alpha and a square root of alpha in the denominator. And the rest are the coefficients, the 4m, the h squared, and the square root of pi end up over there. So that's the ratio. And our goal is to prove that for some alpha, this ratio is bigger than 1. So if this ratio is bigger than 1 for some value of alpha, v is bigger than t, and the expectation value of h is negative, and the ground state energy is negative. So we have our job, the job cut out for us. We just need to show that this thing is bigger than 1 for some value of alpha. So let's do that. I'll push this here. And we'll work with the graph of the function here. So I want to show that this is greater than 1. And the intuition is that we're in good shape, actually. If we don't try to be too rigorous, we could say, well, look, if alpha is large, that's very bad. So you should take alpha small. So somehow you must take an alpha that is very small so that the Gaussian wave function is very spread. And if alpha is small, well, this number is going to be very big. And if alpha is small, it's almost like 0. Well, this integral is some number. And presumably, this number is not too small. And you're okay still. So we're going to try to make these intuitions more precise by using the axioms and doing something more accurate. So what am I going to say? I'm going to say that you could pick some value, some point, since the function is piecewise continuous, there is some point in this potential, some point x0, where the potential is negative, and it's some finite value, and I will call that value, maybe, I will call that value, this depth, in here, 2v0, with v0 positive. So 2v0 is the distance from this point to this point. It's an energy and it's v0 positive. Certainly, in this wave function that we took here, alpha must be positive as well. So here is the claim. If the potential is never positive and it's piecewise continuous, there's some point where it is continuous, and I can just look and see what is the value here of the potential. Now, since the potential goes to 0 eventually, I can draw a line here at V naught down. There's two V naught, so I can draw a line at V naught. So this height is now V naught. And find that it intersects the potentials at 2 points, x minimum and x max. Or, no, I'll call them differently. I'll call them x1 and x2. It's clearer. x1 and x2, with x1 less than x2. And since the function is continuous, these two numbers are not x0 because the function is continuous at this point, so it must take a while until it reaches depth just v naught. You know, it goes even deeper here, but eventually it has to find places where it has depth v naught. And this will be useful for us in order to be very precise about what we're doing. So there's this region here that gets determined. Okay, so let's look at this integral. Integral from minus infinity to infinity of e to the minus alpha x squared v of x dx. I want to show that this is bigger than something because I want to show that this thing is bigger than 1. So this is bigger than the integral that you would do from x1 to x2 of the same function. And this is clear because the integrand is positive everywhere. The exponential is positive and the v is positive. So the integrand is positive everywhere. So if you integrate it over less of a range, you are getting less. So the integrand is definitely bigger. The integral is definitely bigger than this integral from x1 to x2. Now, in the region x1 to x2, the potential is the absolute value of the potential is certainly bigger than v naught because it's deeper. Throughout this region from x1 to x2, it's deeper than v naught. So the absolute value of the potential is bigger than v naught. So I'm sorry, I have the exponential still here, minus alpha x squared dx. And this is bigger than v naught. V of x is always, throughout the integral, is bigger than v naught. So this integral is bigger than, if you substitute v of x by v naught, which you can do. So it's greater than v naught integral from x1 to x2 of, oh, I'm sorry, there's too many e to the minus alpha x squared. I didn't see it. It's here. It's greater than v naught times integral from minus alpha x squared from x1 to x2 dx. Okay, a lot of the complication has disappeared. And, but we're still stuck with an integral that we can't do. And because this integral of the exponential function of Gaussian between two arbitrary points is undoable. So we still want to say things. So I claim that this integral is bigger than the integral from x1 to x2 of e to the minus alpha times, you see, x squared is going to vary here. It's going to go through some values, and it's going to go from some values up to some larger values where this is suppressed even more. The larger the value of x, the more it is suppressed. So the most suppression, so over this integrand, x squared is going to vary, and when x is the largest, it suppresses the integral more. So I claim it's bigger than if you would replace x squared by the largest value that x squared takes in this interval, because that's the most suppression you ever get in that integrand. So if you put the full suppression, so you replace the x squared by the largest value that it takes, then this integral is bigger than what you have here. So mine is greater than the integral dx of e to the minus alpha, and then I'll put here maximum of x1 squared and x2 squared. The maximum of these two. You see, you're integrating over a range from x1 to x2. I don't know which is bigger in absolute value. It's maybe x1 or x2. But the integrand is most suppressed when it takes the largest value, and therefore this is correct approximation at the place here where x, either at x1 or x2 when the integral is most suppressed. But if you replace the x squared by just this number, the maximum value of x1 plus x2, that's definitely going to give you something less than what you are supposed to get. So this is the last inequality that I have. So far, I've proven that, shown that integral from minus infinity to infinity e to the minus alpha x squared v of x dx is greater than the integral from x1 to x2 of this. But now this is a number, so I just get x2 minus x1 times e to the minus alpha max of x1 squared, x2 squared. So we've simplified this matter quite nicely. We still have this alpha dependence, and that's not quite ideal. I've lost the v naught, and now I've recovered it. And we're not quite done simplifying this, because I have an alpha here, and I would rather have no alpha. So think of this factor. And look at what happens if I choose an alpha that is already smaller than something that I'll write here. Suppose if alpha is smaller than 1 over the maximum of x1 squared and x2 squared, then alpha times this maximum is less than 1. So this thing is less than 1. So this number over here in the exponent would be less than 1, and therefore this is bigger, this whole factor becomes bigger than e to the minus 1. So if this is true, I claim that this is bigger than v naught x2 minus x1 times e to the minus 1. Because when alpha is less than that, this product is less than 1. So it's less suppressed than if it would be 1. So this thing becomes a number. So look what we've achieved. We've managed to reduce the potential contribution to say that it's bigger than just one number when alpha is chosen in this way. So this is our conclusion. Now, what does that do for us? Well, let's go back to the ratio. So the ratio now over here, the absolute value of V, psi alpha over absolute value of T, psi alpha, is equal to this quantity, but that quantity is already bigger than 4m over square root of pi h squared 1 over square root of alpha and we have the V0 x2 minus x1 e minus 1. Over E. So the ratio is bigger than that. Okay, we're almost there. I want to make sure I got the right answer and I'm not missing any factors for m square root of alpha h bar v naught. Yep. Okay, now it should become obvious that we have succeeded. You could say, look, whatever this is for alpha sufficiently small, it's going to be bigger than 1. But let's try to make it very precise and in that way understand a little better how you say these things. So let's look at units. Alpha has units of 1 over length squared. Why is that? Because alpha is here, and if x has units of length, the exponential must have no units, and therefore you have alpha having units of 1 over length squared. Therefore, 1 over square root of alpha has units of length. If this has units of length, and this thing, which is a number that doesn't depend on alpha, multiplies it to give a ratio of energies that has no units. If this has units of length, this must have units of 1 over length. So this ratio, this quantity over here, has units of 1 over length. So it can be set equal to 1 over some length L naught. Whatever it is, you read your potential, the x2 and x1, the mass h squared v naught, this must make a quantity that has units of length, and therefore we'll call it 1 over L naught. So what we've, and this L naught is calculable and is alpha independent. Alpha independent. So our ratio has become the ratio of V over the ratio of T, psi alpha is greater than or equal to 1 over L naught square root of alpha, or 1 over alpha L naught squared. So if I choose alpha less than 1 over L naught squared, if alpha is less than 1 over L naught squared, alpha times L naught squared is less than 1, and this would be greater than 1. So greater than 1 if alpha is less than 1 over L naught squared. So now we're done. What do I have to do? I have to choose alpha to be less than the minimum of 1 over L naught squared and 1 over max x1 squared, x2 squared. See, in order to get the first bound to work, it has to be smaller than this quantity. And now it has to be smaller than 1 over L0 squared. So the answer is choose one that is smaller than the minimum. It may be that this dominates or this dominates, but the answer exists. So for some alpha less than that, you get that this ratio is greater than 1. And if that ratio is greater than 1, the absolute value, the expectation value of the Hamiltonian in this state, psi alpha, is negative. The ground state must be smaller than that, and therefore the ground state energy is negative. So this is a proof that you must have a bound state. You could say, how do I know that the bound state exists? Well, that would, if a bound state exists, it has negative energy. Now, if any states exist, if this problem has a spectrum of states, then there's lots of states, and there will be one with lowest energy, and that one with lowest energy would have to be with negative energy. That's what you've demonstrated here. And we took our time to do it as a nice application of the variational principle because it's very general. This is exactly the kind of problem you cannot solve analytically. This is something for which you need a proof that a solution exists. The potential is completely arbitrary, and yes, you can show that the potential with a very little square well has a bound state, and you can show that other potentials may have bound states, but to show that every potential that is attractive has a bound state, you have to do an abstract, complete argument, and that's what we've done here.